Okay, so last week we talked about equilibrium and Le Chatelier's principle, and we talked a lot about the position of equilibrium. And the position of equilibrium seems to be this very vague sort of idea of it being to the left or to the right. And if it's to the left, you get more reactants, and if it's to the right, you get more products. So today, when we talk about the equilibrium constant, we're going to start to quantify what that actually means. So we're going to try and put a number on this idea of the equilibrium being to the left or being to the right. And we do that with this Kc, the equilibrium constant. All right. So we're going to start with the simplest possible equilibrium reaction, which is just one reactant and one product. And the equilibrium constant for this situation would be simply the ratio of the concentration of products to the concentration of reactants. Okay, so here, where we use these square brackets, okay, these square brackets, that's just a really quick way of saying concentration. Okay, so whenever you see these square brackets in a chemistry setting, you should be thinking, well, it's the concentration of the thing inside those square brackets. Okay, and also we want to say that for this situation here, all right, so these concentrations here, these are the equilibrium concentrations. Because obviously what could happen is, if I want B, I could just put A into my reaction system. Okay, then at the very start I'll only have A, but then as the reaction happens and I achieve equilibrium, then I'll have a different concentration of A and a different concentration of B, but they'll stay the same. All right, and it's that concentration at equilibrium that I use in here. Okay, and we use just the normal units of concentration, which are moles per decimeter cubed. All right, so there are three situations that we can imagine for Kc here. Okay, three possible situations. The first is that Kc is greater than 1. Okay, now if Kc is greater than 1, it means that the numerator is larger than the denominator. Okay, so it means that the concentration of B is larger than the concentration of A. So you can imagine that if the concentration of B is larger than the concentration of A, we've got this position where the equilibrium position is to the right. So the products are favoured. Okay, and that would be denoted by Kc greater than 1. The second possibility is Kc is smaller than 1. Okay, now if Kc is smaller than 1, that means that the numerator is smaller than the denominator. All right, the concentration of B is smaller than the concentration of A. Okay, so if the concentration of B is smaller than the concentration of A, that means our equilibrium is over to the left, and we are favouring the reactants. Okay, and that would be this Kc less than 1 situation. And the final situation we could possibly have is Kc is equal to 1. And if Kc is equal to 1, that means that the numerator and the denominator are exactly equal. So we have the concentration of B equals the concentration of A. Okay, so when we're doing these, it won't always be A and B, but you can talk about so if Kc is greater than 1, we can talk about the concentration of the products being larger than the concentration of the reactants. Okay, so as usual with these videos, I'll just do the examples from the book, so it'll be easier for you to follow. So the first example from the book is number 1. It is H2 gas plus I2 gas gives us 2 HI gas. Okay, now Kc is going to be, remember, it's the products divided by the reactants, and it's the products all multiplied together. Okay, so here where I've got 2HI really is the same as HI plus HI, which means that what I can do is I just multiply these two together. So I do the concentration of HI times the concentration of HI. And I divide that by, over here, the concentration of these two multiplied together. Okay? And so that is my equilibrium constant. Now, because these two are multiplied together, I can simplify this, so I can write it as HI squared divided by H2 I2. So you can see that any coefficient that you have in front of a quantity ends up as a power after it. Okay, and you would have seen that when you made your notes written as, so this kind of complicated thing here where you've got the concentration of C to the little power of C. The C is just the coefficient in front of it. Okay, and that's how it comes about, because if it's got a 2 in front of it, it means there are 2 of them, and 2 of them multiplied together is squared. All right, so if we now go ahead and put the numbers in, so the numbers that we were given in the book were for HI 2.28 times 10 to the minus 3 for HI, divided by H2, oh no, I need to square that, it needs to be squared, divided by the concentration of H2, which is 8 times 10 to the minus 4, times I2, which is 1.2 times 10 to the minus 4. Now, you can see that the concentration of HI is an order of magnitude larger. This is 10 to the minus 3. These are both 10 to the minus 4. So the concentration of this is much, much larger than the concentration of these two. So I'm expecting my value of Kc to be at least larger than 1. All right. And if you work that out, you get 54.2, okay, which is obviously much larger than 1. Okay, so I know that I've got more of this than I have of this. And obviously I can compare that to other reactions. So if I did another reaction and I had a equilibrium constant of 50, I know that this reaction lies further to the right. Okay, now something they don't go to in great detail in the book, but which is important particularly later on, is the units of this value here. What are the units? Okay, you'll have noticed that for this one in the book you weren't given any units. Okay, now there is a reason for that, and it is because well, the units for concentration, units for each of these is moles per decimeter cubed. Okay, so we work out the units by substituting in the units for each individual one and then simplifying. So the units for this are moles per decimeter cubed. The units for this are moles per decimeter cubed, divided by the units for H2, which are moles per decimeter cubed, and the units for I2, which are moles per decimeter cubed. So in this situation you can see that these all cancel. So that cancels with that, and that cancels with that, and the units are, well, there are no units. Okay, so you just write it as 54.2. You don't need to write anything after it. You don't have to write no units. You just write it as 54.2, which is what they did in the book. Okay, so they calculated it and they just left it as 54.2. All right, and the reason is because all of the units cancel. Okay, pause it there.